Hello and welcome to week 10 in artificial intelligence. This week we'll be talking about learning probabilistic models. Jumping right in, the agenda for today, we'll talk a little bit about the assignments, and then we'll talk a little bit about chapter 20, which is centered on learning probabilistic models. First, the assignment, and we are in week 10, so the arrow is pointing slightly between weeks 8 and 11. In week 11, you're supposed to be working and turning in a paper on deep learning frameworks. Week 12, you'll be doing a project on learning. Week 14, a natural language processing project. And Week 15, your final paper, which centers on robotic simulations. Do remember to submit your proposal for your projects early so that you have time to get them approved and begin work on them. The papers pick some topic that is appropriate and interesting to you related to it and delve in. The deep learning frameworks, there are quite a few several well-established frameworks out there to consider. Off of top of mind, TensorFlow and PyTorch are the two that pop to my mind. There are a multitude of those, so do spend some time looking around, finding one that either is new to you or something that you think may be relevant in what you may be using, and then go into detail on it. And as always, if you have questions about such things, send me an email or a message, and I'll get back with you as soon as possible. So again, you should be working on your paper for deep learning frameworks, and then potentially looking ahead to the projects which are coming later on. The discussion for this week centers on the topic of the chapter, right? So you pick something out of the chapter that we're discussing, find a real world example of it and talk about it in describing it in your own words. The idea here is that you take it and make it more tangible and real, not just theoretical. Also, as always, these are the useful resources for this course. The top is the website associated with the text. It is a pretty good site. You probably want to spend some time there if you haven't already. You also want to take a look at the GitHub repository that is associated with the code examples and the pseudocode from the text. If you go there and you find something that's relevant for one of your projects, feel free to use it, but make sure you both give credit to it and extend it in some fashion. Take it beyond what is just, don't copy and paste their code and turn it in as your own. Certainly don't do that without giving credit. And try to do something that builds upon what they've done, making some modifications, making sure that you document what you changed, and make sure that those changes are sufficient to count as something that is your own work. If you have any questions about that, feel free to reach out. That's what I'm here for. Modified it. Moving on to chapter 20, which is around learning probabilistic models. Jumping right into statistical learning. The key concepts, and I try to pull out the ones that are central to understanding this topic. One of the first ones is around Bayesian learning, and that's about calculating probability of each of the hypotheses based upon data. And the whole point of that is to enable prediction. And then we'll talk a bit about the maximum a posteriori, which is used to make predictions. We'll refer to that as MAP. I'll try not to say MAP. It should be MAP. Based on the single most probable hypothesis. So again, the most likely sort of thing. Uh, Talking a bit about full Bayesian learning. We view learning as Bayesian updating of a probabilistic distribution over a hypothesis space. And I'm not going to drain the slide. If you're really interested into Bayesian learning, do spend some time reviewing this. Feel free to pause, take a look at it, and move on. The MAP approximation is, with many things, calculating the exhaustive value. The actual value is computationally expensive. So instead, we often approximate it. And again, as the first line there says, summing the hypothesis over most spaces is impractical because that's a really big number. We approximate instead, and we do so using some formulas. And the idea being that it's good enough, right? So that's what we're going for. and you're looking for something that is kind of determined to be a reasonable approximation of the real thing. It's based upon this concept of the maximum likelihood hypothesis, which is being built out here. And another possibility is you may want to take a look at the data that's given. So the maximum likelihood approximation is also discussed, again, related to statistical learning. Sometimes you know all the data, sometimes you don't, and that's where we oftentimes deal with partial data. So you may come up with a density estimation. That's the idea of learning a probability model given data assumed to be generated by a model. So the basic idea here is that you assume that the data is coming out of something. So you try to estimate what that thing is that's producing it. When you have complete data, you have all the data points for every variable. That is not as common as the case of not having them all. When you do parameter learning, you're basically trying to find a numerical parameter for a given probability model with a fixed structure. It's not dynamic. It stays the same between executions or evaluations. So how do you estimate a parameter? And you may do it using Bayes nets, basically. So maximum likelihood parameter learning and Bayes nets. Again, one possible solution. And you may do something with a general naive Bayes as well. Moving on to learning with hidden variables. So the idea of the expectation maximization EM algorithm. General concepts. You have basically a set of the assumption that there is some hidden variables, latent variables that are not observable in the data. They're there, but you can't read them directly. They're doing something, but you try to figure out what they are. Sometimes we'll do things like using unsupervised clustering, which is finding which elements belong to which category. So you can see here in figure 20.1 or 20.12 the various types of approximation of finding those three, what essentially look like three different clusters of points. So left to right, basically using some weights. And in the second one, you're actually kind of looking at the 500 data points from the model. And then the third column over to the right, figure C, is what's constructed using the algorithm. So you can see that it's a pretty good approximation. And with that, we've reached the end of the presentation. If you have any questions, feel free to reach out. A very brief discussion this week. Do focus on your papers. I look forward to reading them. Stay safe, and I'll speak with you next week.